Hi everyone, welcome back. We're now going to focus on a particular kind of generating function, and these are known as the rational generating functions. So we've already seen that this generating function, the generating function for the sequence of ones, can be written in this compact form. It can be written as a rational expression, as a rational function. Polynomial on the top, just happens to be a constant in this case, and a polynomial on the bottom. Generating functions which can be represented as rational functions are going to be the main object of study for this lecture. So here's our definition. A generating function is called a rational generating function if we can write it in the form of a polynomial over another polynomial. Just a reminder, our main interest in generating functions, and in particular in rational generating functions, are the following. Given a sequence of numbers, can we express it as a rational generating function? This is this idea of compression. So we've got a sequence. We'd like to write down the generating function with that sequence as the coefficients of the powers of x, and we'd like to be able to write it in a nice compact form, namely as a rational function. The opposite problem is, suppose we have a rational function. Can we extract the coefficients from that? So this is our coefficient or extraction process. So we've got compression, taking a sequence, writing it as a compact object, namely a rational function, and given a rational function, can we extract the sequence of coefficients from it? That's called extraction. Two of the useful generating functions that we have developed so far are written here. One we've just already indicated. It's the sequence of all ones, so the constant sequence of ones, and we can write that as 1 over 1 minus x. The other one we worked out was the generating function for the sequence of consecutive integers. This we can think of as the derivative of a, or we saw that this is also equal to a squared. So either way we can think about it. And that has this nice compact form. Again, it's a rational function. It's 1 over 1 minus x all squared. So we have two nice compact forms for generating functions for some useful sequences. And those we are going to use over and over again. So let's look at a number of examples. So in each of these examples, I want you to just look at the example and think, is this a question of compression? Are we taking a sequence and trying to write it as a generating function and take that generating function and write it in some compact form as a rational expression? Or is it an extraction problem? Are we given a generating function and we're trying to extract the coefficients from it? So in this first example, we are given a rational function. We'd like to determine the sequence. So this is an example of an extraction problem. So I'll just make a note off to the side here. This is extraction. Well, we can look at this rational function as it's x cubed times 1 over 1 minus x minus a 2 times a 1 over 1 minus x. In other words, I've just taken this denominator and divided it into each piece. Why have I done that? Well, I notice that this denominator, in both of these cases, is this rational function. And I know the coefficients when that is expanded out into its series form. So that's the first step, is to realize that I can break this down into things I recognize. Now for each of these pieces, we can go ahead and write it down in terms of its series. It's 1 plus x squared plus x cubed plus dot dot dot. I write out enough of them so I can generally see a pattern. So 1 plus x squared plus x cubed plus dot dot dot. And now we just want to combine them to form a single series, and this is where we use the ideas from last lecture of multiplying series together adding them up term by term, etc. So here we're going to multiply through x cubed into each of the terms. So I get an x cubed plus x to the fourth plus x to the fifth plus x to the sixth plus dot dot dot. And in the second series, I multiply through by the negative 2. So I get a negative 2 minus 2x minus 2x squared minus 2x cubed, and so on. And now I can add them up term by term. I just noticed in the first one it starts with an x cubed. So I've got these first three terms that are all by themselves. Minus 2, minus 2x, minus 2x squared. And then for the cubed term, I've got an x cubed and negative 2x cubed. So that just becomes a negative x cubed. I got an x to the fourth, and then I'd have a negative 2x to the fourth. So that's just a negative x to the fourth. So every other term just has a negative 1 as the coefficient. And so we get then, what is the sequence? Now I just have to read off the coefficients. The sequence is negative 2, negative 2, negative 2, negative 1, and so on. Another way we can express this sequence is to just write it as what they are. They are the coefficients of the x to the n term. So this is written as the coefficient of x to the n of this rational function is given by, well, there's two kinds of coefficients. It's either going to be a negative 2 or a negative 1. So I can use a piecewise function to describe this. It's negative 2 if n equals 0, 1, or 2. And it's negative 1 if n is greater than or equal to 3. And so there we go. What we've done, again, is we've taken this rational function. It's a generating function, but written in a compact form. So we've taken that generating function and expanded it out as a series so that we could see what the coefficients are. And then we've extracted those coefficients. Let's have a look at another example. Determine the sequence for this rational generating function. Again, this is a question of extraction, coefficient extraction. We have a generating function. We want to figure out what the coefficients are for each of the x to the n's. Again, we notice that this denominator, 1 minus x all squared, that's something we can deal with. If I go back to the previous slide, we know the coefficients of that expression, 1 over 1 minus x all squared. They are the consecutive integers. So we try to use that here. So what we'll do is we'll divide that denominator into each piece. So I get a 2x squared, 1 over 1 minus x all squared, plus a 5 times 1 over 1 minus x all squared, plus a 7x. In this case, I could put the series in like I did in the last example, just plug the series in for each of those expressions. But I'm going to contrast this with showing you how we could use the sigma notation form in this case. So the sigma notation form says, hey, I know what this rational function 1 over 1 minus x squared is as a generating function. The corresponding series is the sum, as n goes from 0 to infinity, of n plus 1 x to the n. And similarly for this other piece, it's the sum, n goes from 0 to infinity, n plus 1 x to the n, plus 7x. So there we go. Now we've just got these two series written out, and we just need to combine them so that we've got a single series, so then I can read off the coefficients. When I multiply the 2x squared through, I just multiply it to each term. So we get a 2 n plus 1, and then it bumps up the exponent on the x by 2, so x to the n plus 2. Similarly for this one, multiply each term by 5, and then the last one we've got just a 7x hanging on the end. It's important to notice that maybe putting parentheses in here just to avoid any confusion. That 7x is just a term added on the end. It's not involved in each term of the sum. And similarly here, we can think about that's just a series, and then that's added to another series, which is then added to that linear function 7x. Okay, so now I want to add these things up. I want to combine them together. One of the issues I see is their powers on the x's don't match. Now, this one over here is 2 ahead of this one. So what I'd like to do is just match them up. So I notice that this first series, it starts at n equals 0. So when I plug n equals 0 in here, I've got an x squared. So essentially it's starting with the x squared term. And I can just adjust it to make sure it starts at the x squared term by starting n equals 2. When I start n equals 2, now I can just leave the n up there because it's going to start with the x squared term. But I need to adjust now this number out front, because for the first term here, when I plug n equals 0 in, I get a 1. So when I plug a 2 in this, I better also get a 1, because it's supposed to give me the same coefficient. Another way to think about this is, whatever the exponent is, the number in front is 1 less than it. So that tells me that I need to adjust that, so it's an n minus 1. And so I've readjusted. The nice thing about this is, once I've readjusted in that way, I can now add these two series together, term by term, because their corresponding powers on x now match. The first one starts with n equals 2, so an x squared term. So I'm going to get some terms from this one that just don't partner with anything. For example, when n equals 0, I get the constant term. So that's going to give me a 5. What about linear terms? Well, I'm not going to get a linear term from this first one because it starts with n equals 2. The linear term from the second one is going to be when n is 1. And so that's going to give me a 5 times n plus 1, or a 5 times 2, which is 10. So I get a linear term from that one. But I also have this linear term hanging on the end. So I also get a plus 7 times x. So there's my linear term. And then from that point forward, we're going to get square terms, cube terms, and so on. And those are going to come from each of these series. So now I can go ahead and write down the sum. As n goes from 2 to infinity, what do we get? We get this one, 2 times n minus 1, plus 5 times n plus 1. So we get a 2 times n minus 1, plus a 5 times n plus 1. And that's times x to the n. And that's going to happen for all of the terms all the way down. And so there is our result. We can simplify that a little bit more. So this is 17x plus, and the remaining terms all form this pattern where it's 2n minus 1 plus 5 times n plus 1. So that's 2n plus 5n, that's 7n. And then a 5 minus 2, so that's a plus 3x to the n. So what is the sequence that this rational generating function that we started with, what sequence does it represent? Well, we've now written it as a series, and I can now read off the coefficients. And so the sequence is, well, it's the coefficient of x to the n, 2x squared plus 5 over 1 minus x all squared plus 7x. That coefficient depends on where we are. So it's either 5 if n is 0, or 17 if n is 1, or otherwise it is 7n plus 3 if n is greater than or equal to 2. And so there we go. We have found the sequence that this rational function represents. So this rational function is the compact form of the generating function, which is defined by this sequence. So now I want to just extend some of the things we can do with generating functions algebraically. So if a of x is the generating function, which defines the sequence A naught, A1, and so on. Then what we can do is we can plug in for x an expression involving x. So I'm not plugging in a number, but I'm just modifying the x. I'm plugging in an expression, c times x to the m. And what that does is it just plugs c times x to the m in for everywhere I see an x. What this has the effect of doing is essentially spacing out, creating a new sequence which is now spaced out. Because it's got a constant term, now the next term comes from x to the m. And the next term after that comes in front of the x to the 2m. So we've spaced it out. There's zeros inserted between the constant term and the x to the m term. There's zero coefficient spacing them out. So what we've done is we've taken our sequence and we've spaced it out through this technique of substitution. This allows us to describe more generating functions in a compact form. So for example, if I look at this Nichols generating function, 1 plus x to the 5 plus x to the 10 plus, maybe I'll add a few more, 15 plus x to the 20 plus dot dot dot. I can write this as, well, it's 1 plus, and then I'll just group together the x to the 5 as like a single object. Because then x to the 10 is that object squared, and x to the 15 is that object cubed, and x to the 20 is that object raised to the 4th power, and so on. And so this looks very much like the generating function a with x to the 5 plugged in for x. So where a of x is that generating function that I named way back at the beginning of this lecture, 1 plus x squared plus x cubed plus dot dot dot, our generating function for the sequence of all ones. So it looks like this n of x generating function can just be obtained from a by plugging x to the 5 in. And that's nice because we have a nice compact form for a. It's 1 over 1 minus x. So a of x to the 5 is 1 over 1 minus x to the 5. And so there's a nice compact form for n of x. And we got it by using one of our known generating functions and its compact form and substitution. We plugged in an x to the 5 into that known expression to get the generating function 1 plus x to the 5 plus x to the 10 and so on, and its closed compact form. Let's have a look at some more examples. What is the generating function for this sequence? So this is a question of compression now. We have a sequence. We want to write down a generating function, and in fact we'd like to write it down in a rational form, so a nice compact form. So how can we do that? Well, this sequence gives me the generating function 1 minus x plus x squared minus x cubed plus x to the 4th minus x to the 5th, and so on. So that's just writing down, if that's the sequence, here's the generating function, because I use those as the coefficients. But then I can recognize that this is 1 plus, and then I'll just group together the negative with the x. It's 1 plus negative x plus x squared is the same as negative x squared. Negative x cubed is the same, well, maybe I should say it this way. Negative of x cubed is the same thing as negative x all cubed. X to the 4th is the same as negative x to the 4th. So in other words, when I take a negative and raise it to an even power, it becomes 1, but I raise it to an odd power, it becomes negative 1. That's all I'm using here. And then that's negative x to the 5th, and so on. And so then I recognize that this is my generating function with negative x plugged into it. So that's my generating function for the sequence of all ones, but I've just plugged negative x into it. So this is 1 over 1 minus, and then I've plugged negative x into it. Or in other words, it's 1 over 1 plus x. And there we go. we've taken this sequence of alternating ones and negative ones, and we've written it as a generating function in a nice compact form. Let's do the next example. Let c of x be this generating function. We want to write it as a rational function. C of x is equal to 1 minus 2x plus 4x squared minus 8x cubed plus 16x to the fourth. We can do the same thing we did above. The idea is we just want to try to recognize lurking behind the scenes here is one of these generating functions, one of these series we already know. And if we back up, what series do we know? We know these ones. So we're always trying to find these ones lurking behind the scenes. In particular, 1 plus x squared plus x cubed and so on, or the corresponding series where the coefficients are consecutive integers. Let's see if we can find those lurking behind the scenes here. Well, if I group the negative 2 with the x, then that's the pattern that can follow all the way down. Negative 2 with the x, all squared, that becomes the 4x. I can group together the negative 2 with the x, all cubed, that becomes the negative 8x cubed. Group together the negative 2 with the x, raise it to the fourth power, that's the 16x to the fourth. So we see that this is just 1 over 1 minus whatever was plugged in, substituted in for an x in the expression for the generating function we know, which is that 1 plus x squared and so on. And so that becomes this, 1 over 1 minus negative 2x, or in other words, 1 over 1 plus 2x. And so there's our rational expression, our rational function. That's the compact form for this series. Let's find the rational generating function for this sequence now. 1 minus 2 plus 3 minus 4 plus 5 minus 6 and so on. So again, this is a question of compression. So let's write it out as a generating function in series form. It's 1 minus 2x plus 3x squared minus 4x cubed plus 5x to the fourth minus 6x to the fifth plus and so on. It's nice because it's got these consecutive integers going up, but the problem is this alternating sign. So I can deal with that alternating sign. I can just group it with the x. So I'm just going to stick a negative in front of the x in all cases. And it works out nicely because when it's stuck in front of the x for an odd power, that's where the negative actually appears, in front of the odd powers. And so just grouping it with the x causes that to happen. It's positive in front of the even powers, and that's fine because when I take a negative, raise it to an even power, it becomes positive. So this captures it precisely. So this becomes 5 negative x to the fourth plus 6 negative x to the fifth, and so on. So that's nice because this is our second generating function we want to use, the generating function for consecutive integers. That would be 1 over 1 minus whatever substituted in squared, and in this case it's a negative x. So this becomes a 1 over 1 plus x, all squared. So that's the generating function for the alternating sequence of consecutive integers, 1 minus 2 plus 3 minus 4, and so on. Let's do another example. Express d as a rational function. So again, this is our question of compression. So I'm just having you think about what is the question actually asking. Do we have a sequence and we're trying to write it in a rational form, a nice compact form, or do we have a compact form and we're trying to pull out a sequence? In other words, is it a compression or an extraction question? And this is a compression question. Take the sequence, write it in a nice compact form. So d of x, well, I can see that since it starts at x, then x is a common factor of everything. So I can pull that out front. In fact, I can pull the whole negative x out front. and then I just write what's left over. Well, now there's a 1, a minus 2x plus 3x squared minus 4x cubed plus, and so on. So I just factored out a negative x from every term. We can either recognize that this second factor is the one we had up above, or we could do the same thing that we did up above by grouping the negative with the x now. And I'll just do it that way. So we group the negative with the x, and now I notice that that's the generating function for the sequence of consecutive integers with negative x plugged into it. So this is 1 over 1 minus negative x all squared. And so this becomes negative x over 1 plus x all squared. So there is our nice compact form for the generating function, which represents the sequence 0, so there's a constant term of 0, negative 1, 2, negative 3, 4, and so on. Okay, so with the idea of substitution, we can now do the general process of extraction. We now have a method for extracting from any rational function of this form, so polynomial over a linear function, or polynomial over the square of a linear function. We can now extract the coefficients for anything of that form. Let's see how we can do that. So we've got c of x. We now want to do an extraction problem. What are the corresponding coefficients for the powers of x? What sequence is this irrational generating function for? So it's asking us to find the coefficient of x to the k. So what I'm going to do is I'm going to factor out an x squared, and I really want to be able to find in the expression something of the form 1 over 1 minus x or 1 over 1 minus x all squared, because those are the two rational functions that I know the generating functions for. So can I do that? And the idea is, yeah, absolutely. What I can do is I will factor out an x squared, so there's a 1 on top, but I factored out a 3. I factored out a 3 so that I could get a constant of a 1 on the bottom. I'm just going to switch the order of the denominator terms, and a 2x over 3. So just notice that the way I've done this here is that if I was to multiply this in, I just get 3 plus 2x. In other words, I get this denominator. So I factored out the 3, and the reason I've done that is because now if I just sort of take a big picture perspective, this is 1 over 1 plus something. And I'll deal with that something in a second. But it's of the form of the rational function that I know the generating function for, that I know the sequence for. 1 over 1 minus x is the thing I'm looking for here. So I can get even closer to that by writing it as 1 over 1 minus negative 2x over 3. And there we go. So that says, hey, I know that. I know that is the rational function for this sequence. 1 plus negative 2x over 3 plus negative 2x over 3 all squared plus negative 2x over 3 all cubed plus, and so on. And so this becomes 1 plus negative 2 thirds x plus negative 2 squared over 3 squared times x squared plus negative 2 cubed over 3 cubed times x cubed, and so on. Might be nicer to write this using sigma notation. So this goes n equals 0 to infinity of negative 2 over 3 to the power of n x to the n. And then I can multiply through by x squared over 3. So this becomes the sum n goes from 0 to infinity. It now is an x to the n plus 2. I've got a negative 1 to the n. I've got a 2 to the n. And I've got on the denominator a 3 to the n, but this other 3 comes over as well. So that becomes a 3n plus 1. And so there we go. We've written it as a series. One thing to note, though, is the power on the x. It's n plus 2. If I want to extract the coefficient of x to the n, I'm going to have to do some fiddling with what the expression would be. So what is the corresponding coefficient if this was an n here? So I might as well make that adjustment now. I'll make the note that since the first term is x squared, then this is going to start with n equals 2, go to infinity. So I'll replace the exponent on the x with the n now. And then the thing I notice is that I have to update these other n's. So what I've really done is I've replaced in this expression, I've just replaced n with n minus 2. So I would replace this n with n minus 2, I'd replace this n with n minus 2, and I'd replace the n in this expression with n minus 2. But if I drop the exponent on the negative 1 by 2, that doesn't change its parity, so I might as well just leave that as an n. But this I would have to drop by 2, the exponent on the 2. And the 1 on the 3, I would have to drop it by 2. So it would become an n minus 1. And so now we're perfectly set up to extract the nth coefficient. The nth coefficient, because it starts at n equals 2, we know the first two are going to be 0. So it's 0 if n equals 0 or 1. And it's negative 1 to the n, 2 to the n minus 2 over 3 to the n minus 1 if n is greater than or equal to 2. And so there we go. We've extracted the coefficients. We had a rational function. We have now written it as a series, and we've pulled out the corresponding coefficients. 0 for the first couple, and then that's the pattern for the remaining ones. Let's have a look at one more example. Find the coefficient of x to the k in this generating function. Can I spot a 1 over 1 minus x squared in here, or 1 over 1 minus something all squared in here? Well, let's see if we can do that. I'm going to factor out an x squared. That leaves me with a 1 up top. And I'd really like this to be of the form of 1 minus something. And then we've got the square out there. So the question is, what's going to go here? What do I put in that box? Well, if I take this 2 and I factor it out, I pull it out. Well, it's caught inside a square, so when I factor it all the way out, it comes out as a 4. And that is going to leave me with a 1, so I just happen to move the 1 to the left. But then I also have an x over 2. So then that gives me an x over 2 there. But I wanted, right now it's a plus x over 2. I want it to be a minus x over 2. So that's where I put the extra minus sign in front of it. And so there we go. What I've done is I've just done a little bit of algebraic manipulation to get it in a form that is going to be useful for me. If you're wondering, did this work? Did we get it in the right form? Well, we can just expand it out. X squared times the 1. That gives me the x squared. Great. 4, when I expand it out, well, 4 is 2 squared. And so when I bring the 4 inside, it comes in as a 2. And I get a 2 there. And I get a 2 multiplied here, which cancels with that 2. And a negative gives me a plus x. So I get a 2 plus an x all squared down there. So this is it in factored form, or at least in the form that we wanted it in. And so now we can continue on. This becomes then x squared over 4, and this is the rational function for this series. N goes from 0 to infinity of, the coefficients are consecutive integers, so n plus 1, and then it was a substitution of that known series we had where we substituted negative x over 2 in for x. And so that's it to the power of n. And so there we go. Now we'll just clean it up a little bit. N equals 0 to infinity. We get a negative 1 to the n. We get a 2 to the n on the bottom. We get an n plus 1. We got an x to the n. Then I can expand through. So this thing out front, I just multiply it into each term. What do we get? We get negative 1 to the n plus 1. That's an x to the n plus 2. I multiply the denominator by 4, which is a 2 squared, so this becomes a 2 to the n plus 2. Again, this is now the thing shifted over. So I'd really like this exponent to be exactly what the value of the index is, because when I go to search for the coefficient of a particular value, like what's the coefficient of x to the 5, for example, well, you'd have to go, oh, x to the 5, that's when n is 3, so I'd have to use 3 in here. It's a little bit easier if we just write it with x to the n as our exponent. So how do we do that? Well, we just notice that because x starts with a square, we just start our n value at 2. And then we just update all of these other n's. So now, again, the thing I noticed is I'm really just taking n and replacing it with n minus 2. That's not going to affect this one because it's just detecting whether that is positive or negative, so I can leave it as an n. But this would become n minus 1, and this would become a 2 to the n. Or another way to think about this is whatever the exponent is here, this one is 1 less than it. And whatever the exponent is here, this one is equal to it. So if my exponent is n, this one has to be n minus 1, and this one has to be n. So now we've written it as our series, and we can go ahead and extract the nth coefficient. It's right there for us to get a hold of. We just need to be careful that we notice the series starts at n equals 2, so that means the first two are 0. So if n equals 0 or 1, the coefficient is 0. Otherwise, it's negative 1 to the n minus 1 over 2n. And that's if n is bigger than or equal to 2. And so there we go. Starting with a rational function, we were able to write it as a series and extract the corresponding coefficients. So what kind of a problem was this? This is an extraction problem, a coefficient extraction problem. In the next lecture, we're going to go and do more extraction problems. We're just going to start to generalize these results. All right. Thanks very much for watching, and we'll see you in the next lecture.